All right. Well, thank you, Wes, and welcome everyone to Protecting IPMX Content. Well, as was said, I'm Andre Testa, and I will be your presenter for the next 20-25 minutes or so. I'm the ASIC and FPGA Group Manager at Matrox Video. I've been employed by Matrox for the past 23 years. Been driving our product development for ST2110 in the broadcast market and heavily involved in IPMX since the beginning of the effort, participating in many trade shows, Manning's, the AIM booth at those shows, doing presentation, last one being at the Tech Fest earlier this year. Always fun to do those presentations, but quite frankly, I'm missing the good old days of the face-to-face events. I was really looking forward for NAB this year as I was doing a IPMX for broadcast presentation, but well, sadly, we all know what happened. So luckily, next time will be the good one. Okay, the first two presenter kind of did a little background, but if some of you didn't have the chance to look at them, I always start with this. What is IPMX? So the backbone of the proposed solution here is comprised of standards and specification, namely ST2110, which covers the transport of the stream, and the NMOS API suite, which covered the network management, basically how the devices are registered and discovered on the network, how they're subscribed and controlled, amongst other things, providing an API to perform all of those. So as said earlier, the first deployment happened in the broadcast and media industry. It is there. It works, widely adopted. The ProAV market is facing the same AV over IP shift. And as such, the idea here was to leverage the work already accomplished and built on it by incorporating those specific features to the ProAV market. And this is why we call this whole effort IPMX. So there's a few of those particularities there. Jean covered previously the asynchronous sources or signals, the relaxed PTP requirement, support of gigabit Ethernet through compression, HDCP, EDID management, network resiliency, IO expansion, and others. This is just to list a few. So like I said, Jean previously covered the asynchronous signals. This current presentation will deal with the support of content protection. So a little bit of history, just to put things into perspective. So many years ago, with the increased popularity of digital video interfaces and the widespread availability of digital content, this has made content provider increasingly concerned about unauthorized copy and use. So as a result, those content providers, along with the media and electronic manufacturers, have implemented a variety of content protection technologies that protect access to their high-value distributed content. HDCP is part of this chain of protection. So to protect this content, it uses authentication and encryption techniques. Initially, one of the main or more popular interface was HDMI. And as a consequence, the consumer electronic ecosystem has rapidly adopted HDCP for it. Many major manufacturers are incorporating HDCP into their product. Just to give an idea, to this day, roughly 3 billion HDCP device keys have been shipped to date. Those manufacturers, they require a license to implement the HDCP specification, which was originally developed by Intel Corporation and is licensed as a digital output protection technology for audiovisual content. Digital Content Protection LLC, commonly named the DCP, is authorized to license the technology to manufacturers. HDCP adopters or licensees must implement HDCP products that comply with the specification and license agreement, and obviously construct them so that they can interoperate with other products over standard interface. So how does HDCP fit into the overall content protection picture? A variety of technologies and standards have been developed to protect specific types of media. Each of these technologies hand off to HDCP for the last step, which is basically the transmission of the content via a digital interface to the display device. So for example, content providers use conditional access technology to prevent unauthorized access to their content as it is transmitted from the provider to a set-top box. HDCP then protects that content as it is transmitted from that set-top box to your television. The role of HDCP is to prevent the interception and copying or other unauthorized use of this bit stream. So at first, HDCP was designed to operate over certain digital interface like you are seeing in that slide. So HDMI, DisplayPort, and a few others. But more recently, a version of the spec was made to address any wired and wireless interfaces. So one example is that it can be applied for the protection of audiovisual content over an IP-based interface. So devices are basically divided into three categories in the HDCP topologies. So you have your sources. The source sends the content to be displayed. So an example can be a set-top box, a Blu-ray player, your computer video card, or even a game console. There's the sinks. The sinks renders the content for display so it can be viewed. Example there's your TV, digital projectors, or even computer monitors. In the middle can be a repeater. A repeater basically accepts content, decrypts it, and then re-encrypts and retransmit the data. It may perform some signal processing, such as up-converting video into higher resolution format, or splitting out the audio portion of the signal. Repeaters have both HDCP input and output interfaces. And a very common example here can be your home theater audiovisual receivers that separate and amplify the audio signal while retransmitting the video for display on a TV. A repeater could also simply send the input data stream to multiple outputs for simultaneous displays on several screens. There are some particular rules that the repeater must respect, though. They are permitted to convert signals from one interface to the other. Let's say it gets an HDMI signal in, can output a DisplayPort out, but the level of encryption must be maintained throughout the chain. The HDCP protocol can be separated into two main parts, the authentication and the encryption. So before being able to decrypt HDCP protected data, the receiver device initiates an authentication process with the transmitting device to confirm that it is authorized to receive that data. Each HDCP transmitter and receiver includes device private keys. These keys are unique, highly confidential, and not available to other devices. Receivers also include a receiver ID needed to uniquely identify the devices. Both of those are exchanged and used during the authentication phase. There's an extra step involved in if the receiver is a repeater. It is required to send to the transmitter a list of all the downstream receiver IDs. And this step enables the transmitter to determine whether all devices in the tree are valid. The transmitters and receivers also implement a common HDCP cipher, an algorithm that encrypts and decrypts the data. The cipher is used into both processes. So once the receiver has been properly authenticated, the transmitter encrypts the data stream to prevent eavesdropping and sends it to the receiver. This is performed using its HDCP cipher engine and the shared session key to create a stream of encrypted data that can only be decrypted by the receiver. The receiver uses obviously its own HDCP cipher engine and its copy of the session key to decrypt that content. So this kind of completes the general overview of HDCP I wanted to give. Now let's see its usage in the ProAV industry. There are several use cases in the ProAV industry that requires the support of HDCP. So in an attempt to give a little concreteness to this presentation, I will try to list a few here. So my first example will bring us in the control room environment. So it could be a 911 emergency management center, a military and intelligence center, or even potentially hydro and gas distribution management center. So in those places, it is not uncommon to get feeds from live news like CNN or BBC, just to name those. These feeds can provide crucial information as they broadcast live data from the ground in emergency events. Such feeds could come from a setup box in those facilities, or even a player application running on the desktop of the controller. Bar venues offer also a few interesting use cases. So from a digital signage angle, on the screen that you're broadcasting your football game, you can have a side or bottom messaging selling the drink and menu specials, and maybe advertise your specialty nights coming up. Again, in the sports bar environment, you capture the HDCP signal coming in and either place it anywhere within your video wall, or even stretch it on your entire wall. Since it requires to splitting the signal on multiple monitors, your devices will require to decrypt first, then alter the signal, scale it, or even take a portion of it and encrypt to transmitting for the display device. The last example I wanted to give was in a KVM scenario. So we are seeing this more and more, that some systems, even if HDCP is not required for its content, they encrypt the content of their desktop altogether. So one of the reasons is they do not want to disturb the video signal in case the user starts playing content which require HDP protection scheme at that specific moment. So how do we enable IPMX with HDCP for content protection? So the basis is clearly the existing HDCP interface independent adaptation specification, which already applies to IP-based network, as said earlier. An amendment to the specification, named the HDCP Direct Adaptation Amendment, was adopted in May of this year to specifically target the protection of audiovisual content over RTP, which is the protocol used in ST2110. So it provides all the necessary protocol details to transport protected content over RTP streams. But it also details the protocol control messages to exchange among the HDCP transmitters and receivers. However, it's lacking the precise mean to effectively exchange those required messages. And this is the reason why the Key Exchange Protocol, or HKEP, is under development currently at VSF. The goal is providing all the necessary protocol and implementation details that are missing from the Direct Adaptation Amendment to really obtain a fully specified protected content control solution. So with the combination of those specifications, an ecosystem of cross-vendor devices will be capable of streaming protected content over IPMX-based network. The transport aspect of it is covered by the Direct Adaptation Amendment, in which HDCP support is expanded to the RTP protocol. The previous version of the spec was based on MPEG-2 protocol. This amendment uses an analogy to pretty much map the MPEG-2 protocol to an RTP stream, keeping the protocol very coherent one versus the other. Having the same cipher, the requirements are pretty similar. So without going into details here, when I showed the slide to Jean, he told me, man, you're going way too deep. So don't worry, I won't add a lot of details. But the point is, we're using AES 128 counter mode. Therefore, the counter values must be sent to the receiver along with the encrypted data for it to be deciphered and retrieved. The method used to send those counters on each RTP packet is the already existing RTP extension header. And as a final note on this slide, I'll just add that the transmitter is required to assign a unique stream counter value for each RTP stream. And I'm giving this detail because it's going to come handy later in the presentation. All right, so here I'm showing a very quick example on how the encryption is done. So you start with an HDCP data unit, HDU. And in this example, we want to encrypt a video stream, a non-compressed video stream. So an HDU is basically a complete video frame. It is then divided into 128-bit blocks. Remember, our cipher is AES-128. Those 128-bit blocks are placed in RTP packets in order to get each RTP packet to carry an integral number of 128-bit blocks. It's basically the principle. All right, so next aspect to address is the control layer. What is the objective here? Basically, enable IPMX devices to distribute HDCP content between themselves over a multicast IP network. The protocol aims at being as efficient and lightweight as possible because these devices are expected to vary a lot in terms of capabilities and processing power. One of the prerequisites is keeping compliancy. So there's no use or need to change what is already adopted. The intent here is to define how to use the direct adaptation amendment in an IPMX environment. No changes, alterations, or replacement to the existing standard. We need to claim a full compliancy to those standards. And what is the motivation to put such specification together? Again, ensure interoperability between the various IPMX vendors. So in short, those specifications cover the exchange of HDCP control messages over TCP IP among NMOS-based transmitters and receivers. So to make a quick relation with the current HDCP topology, I put a simple diagram which shows there your set-top box being the HDCP source. You have an IPMX sender receiving an HDMI HDCP input and retransmitting it on your IPMX network, acting as your HDCP repeater. Same for the IPMX receivers on the other sides, which are basically doing the inverse. And at the complete end, you have your monitors, your HDCP sinks, which displays the content for you to see. Obviously, HDCP protection has to be kept at every step of the way. Before diving into the actual protocol, let's make a parallel with HDMI. So with HDCP on HDMI, the cable provides two independent channels, the TMDS media channel to transport the content and the I2C channel to transport the status and control messages. With HDCP on RTP, there's a similar model where the RTP stream provides your unidirectional multicast media channel to transport the content. And the TCP IP provides a reliable channel to transport the status and control messages. The TCP IP and RTP channel may reside on the same or even on different network interfaces of a sender or a receiver. So the major distinction between the two systems is that an HDMI cable permanently and persistently connects your HDMI output to an HDMI input connector. It's a peer-to-peer connection where both the transport and status and control messages and media content are interrupted when the cable is disconnected. On the opposite, in an HDCP on RTP stream, the TCP IP connection between the transmitter and the receiver is neither permanent nor persistent. And the multicast RTP media channel represent a one-to-many distribution system. So that's why a disconnect of the TCP IP channel does not interrupt the transport of the media channel. A listener unsubscribing from a media channel does not interrupt the transport of media content, nor the status and control messages, by the way. So now what is HKEP doing precisely? The HKEP protocol describes a preamble to the direct adaptation amendment protocol. It prescribes the expected behavior and optional aspects of this protocol. It also describes the interaction of sender and receivers implementing this same protocol. How does it do it? So it starts by establishing a connection between the sender and the receiver. And once done, it simply tunnels all the messages required, which are already defined in the direct adaptation amendment specification. It also defines the way to terminate your HDCP session. So simple walkthrough of the sequence here. So the receiver gets the SDP transport file of the subscribed stream. Using this information, the receiver initiates an HKEP to establish a connection. And once done, simply tunnels direct adaptation amendment protocol. So once an HKEP session becomes valid, hence your HDCP over RTP session becomes valid, further timeouts, disconnects, or protocol errors shall not invalidate the session. The session shall not expire unless it becomes inactive or the receiver unsubscribed from the associated HDCP content. Senders and receivers shall cache their active HKEP session, and the sender shall reuse this cached session unless it becomes inactive or expired. And the same for the receiver, it shall reuse the cached session unless it becomes inactive or expired or the receiver set the restart. And this particular feature permits much faster reconnection as authentication has already been performed the first time the connection was established. And this is mentioned because terminating the TCP IP connection does not mean that the HDCP session is terminated. When the TCP IP connection is terminated, only the receiver has the ability to reestablish it. So that being said, if for some reason a session key update is required, for example, the transmitter needs to notify the receiver, it must use the stream counter. So remember that small note that I did when we covered the RTP protocol there, where the transmitter needed to assign a unique value to each RTP stream. The receiver must therefore monitor the stream counter value received along with the subscribed IPMX media network. A change in this stream counter value indicates that the state of the associated sender has changed. The receiver must therefore reconnect with the sender and execute the HDCP over RTP protocol all over again. All right, so this was HDCP in IPMX in a nutshell. So the takeaway I want to make on this topic is that HDCP is already widely adopted. It's evolving to match the new use case. It's definitely required to support in many use cases currently happening in ProAV. IPMX is working on incorporating it into its workflow. And as a final note, I can even add that this could be adopted by ST2110 devices as well, since it's all based on open standards and there's really nothing specific to the IPMX environment here. So that concludes my presentation. Thank you very much.
Thank you, Andre. That was really informative. So want to encourage the audience here to ask any questions that you might have. You can use the chat window for that. If you want to have me turn on your video, that's fine too. I did have a question myself, Andre.
Yeah.
One of the things that I think you sort of mentioned in passing is that you have a version of this HKEP or HDCP over IP working today. Could you elaborate on that a little bit more?
Well, currently, we're basing everything on the direct adaptation amendment which was released on the DCP site currently. So all the spec is there. We took this, and currently at VSF, we're working on this HKEP specification, just to make sure that we tie all the knots there and to ensure interoperability. That's the whole point of this effort. As far as actual device working on it, obviously at Matrox in the lab, we're rehearsing all this. So we have this protocol working in our facility. And what we hope to do is in upcoming trade shows, we'll be able to show demos with interoperable devices with this cross-vendor ability, right?
So is there any noticeable connection time required in your lab, or is it just about just as quick as getting HDCP working on regular HD-based or any of the other protocols?
Well, one of the aspect is I didn't name it, but the authentication there, that's the longest part. And this is why I said we try to make this as lightweight as possible, because some devices, like, they don't have this big Intel processor to leverage, its performance there. So we have small processors. So what we do to increase the speed is we have this pre-pairing mechanism where once the connection is established, we pair the device. So it's already authenticated when the streaming is really needed. So that's one of the main way that we use to speed up this process.
Okay. So as soon as the device is connected to the network and you know where it's going to get content from, you can start the authorization process.
Exactly. And once this is done, then the two transmitter and receivers recognize themselves. And so authentication is not really needed every time they need to talk together.
All right, that makes sense. Okay, that's a clever. And do you think that's going to be part of the standard, or is that kind of outside the scope of what we're working on in the VSF?
No, it's going to be covered by the HKEP technical recommendation that we're working on.
Cool. Well, that'll be fun. It's always exciting when you get all these encrypted things up and running. It's kind of sometimes it's a little bit of magic. It's like, oh, let's hope this works.
Yeah. Well, that's the goal, right? It's to like we said, tie all the knots there. Say, okay, you want to do HDCP, do it this way, because there's many ways to do it, and that's the whole point behind our effort. Not just HDCP, right? IPMX. There is, you want to be IPMX, then use the standard in this way. Like Jean was telling in his presentation. Well, IPMX has the same point of view. All the tools are there. You want to interoperate with other vendors, do it this way. He's going to do it this way as well.
So just another question: how difficult is the registration process vis-a-vis getting your device approved or your company approved by the HDP powers that be? In other words, is that something
DCP?
where you?
Yeah, well, the process is pretty straightforward. You just need to sign their license agreement there, and once this is done, you just acquire a key in a bundle to them. They sell them in bundles of like 1,000 keys or 10,000 keys or 100,000 keys, if that's your requirement. And this is a pretty straightforward process once all is signed and put in place.